Alright, welcome back to 3 Deviations. In today's video, we begin Unit 3. So Unit 3 is called partial differentiation, or partial derivatives, forgetting what I called it. But so we are now in new material land. We covered everything we need to about three-dimensional space, vectors and vector functions, and parameterization and polar coordinates in the first two units. So now we're actually ready to go into new material. So this is really, if we are talking only about multivariable calculus, we only have two units that we need to cover, and that's partial differentiation and multiple integrals. However, we usually like to throw in some introductory units for vector functions in three-dimensional space, and then we also like to throw in vector calculus as well, because that's very important to modeling our world. But anyways, now we're in the place where we can start covering new material in multivariable calculus. So we're going to start that by just introducing multivariable functions. We will be working with multivariable functions for the rest of our course. So it's good that we understand what they are and how we can interpret them. So we can define a function of two variables as a mapping that assigns each ordered pair x, y in a domain D to a real number f of x, y. This can be written as f of x, y is such that it is assigned from an ordered pair that is in a domain D. Okay, so what do I mean? I mean that if we have a three-dimensional graph, we have a three-dimensional space, I have some domain D, and this domain could maybe be a rectangle. This is in the general case, so this is domain D, and then above it, every point in domain D is assigned to some sort of surface, or is assigned to some real value in the z-axis. So what this usually corresponds to, almost always corresponds to, is some sort of surface that we get. So this is our function over domain D. So each xy is associated to some z. So that should make sense. And now two-dimensional functions have the benefit of being still able to visualize because they can be represented in 3D space. However, we can have functions of x, y, z. We can have functions of x1 all the way down to xn. That's still a function. But a three-variable function, for instance, takes in any point in space and associates it to some other point, w or something like that. But unfortunately, that's in 4 dimensions, so we can't really visualize it very easily. So we usually try to use the majority of our interpretations for two-dimensional or two-variable functions, because that can still be visualized. So let's try an example, and then we'll call it a day for today. So I'd like us to find the domain of the following function, f of x, y is equal to the square root of 9 minus x squared minus y squared. All right, so we know that in order for our function to be defined, the square root needs to be positive, or the argument in the square root needs to be positive. So the domain says that the stuff inside of the square root needs to be greater than 0. So 9 minus x squared minus y squared is greater than 0. Thus, we can solve for x squared plus y squared, and that will be less than or equal to 9. So what we have here is we have some sort of, in two-dimensional space, we can draw our domain. So we have y and x. And what we have here, you'll recognize this is the equation for a circle centered at 0 with a radius of 3. So we've got a circle here, the radius of 3, and any point that lies within this circle is defined. So this is where a function is defined. And then what we want to do is we want to find the range. So the range is going to be z, such that z is equal to the square root of 9 minus x squared minus y squared. Again, that needs to be greater than 0, so we set that greater or equal to 3. Okay, so now we know that z is going to be between 0 and 3, so we can graph our function, and it's pretty much like a half sphere. It's a half sphere with a radius of 3. So that's really how you graph and think about these multivariable functions, how you can find the domains and ranges of them. Now, because we have three-dimensional functions, we can also use level curves to describe them. So the level curves of a function f are curves with the equation f of xy is equal to k. So essentially what we do is if I have a three-dimensional function, I take a slice of that function, and then what I get is some sort of trace. So let's say I have an ellipsoid or something that we discussed earlier. Well, if I take a level curve for maybe f of xy is equal to 0, then I'll be left with some sort of elliptical level curve here. So it basically shows us where at different levels, at different z levels of our function, it shows us what our cross section looks like. That's what a level curve will do, and it's very helpful for graphing these functions. So that's really what we have for multivariable functions in terms of domains, ranges, and level curves. So in the next video, we are going to introduce the idea of a multivariable limit. So multivariable limits are different animals than single variable limits. We need to use a lot more rigorous proofs in order to prove they exist, and normally they don't exist. So we'll talk about that in the next video. So we'll see you guys then. Bye.